So I'm just going to start reviewing uncertainty, just do a quick review of, it was really Friday and Monday of last week, Friday 2 weeks ago and Monday of last week, that I introduced some of the core principles of uncertainty, and I kind of was rushing towards the end, I knew that. But anyway, so I'm going to finish it up today, but I need to review a little bit. And one way to review, of course, is to remind you what an expectation value is, and again, that is the integral of whatever the wave function is, and of course you have to be given that. And we're still in one dimension. I think next week we'll go to 3 dimensions. It's one thing that's nice. The only thing nice about quantum mechanics is that when we go from wave function in x and we go to x, y, and z, it's actually very easy. It's so easy that I just don't even bother with it till the very end. You just get the same integral 3 times. One for x, 1 times y, 1 times z. It's incredibly trivial. Then when we get to rotation, it gets harder. Anyway, so I have to give you the wave function, I have to give you the operator. You have to simply look up the identity, and there you go. Now that was important because recall that sometimes, and I realize I'm kind of mixing up my symbology, maybe not. Now remember that wave functions, I tend to express them this way. Okay, here's the eigenvalue equation. I tend to use a psi for the wave functions of the Hamiltonian, because again, we think these are important. This thing here and this thing are both wave functions. They are eigenfunctions of different operators. This is the I don't know operator, any other operator other than the Hamiltonian. You've seen momentum, position, kinetic energy. There's about 9 others that we'll go over. There's angular momentum. Unfortunately, there's angular momentum in x, y, or z, and they're not the same. They're actually pretty different, which is weird, but it's true. Total angular momentum, angular energy. So anyway, so there's a bunch of operators, and here's its eigenfunction, and it's because it has an eigenvalue. And again, we think of the wave functions of the Hamiltonian. They're just eigenfunctions, but they're a little bit different because they're a little bit more special. We think of these as the real wave functions. When you saw 1s, 2s, 2p, 3s, 3p, 3d orbitals of hydrogen in freshman chemistry, they were calculated, those were wave functions of the Hamiltonian, not of something else. Anyway, okay, now, I guess I didn't actually mess up my symbology because you know that the problem comes down to, sometimes you apply this other operator, and let's say for the hell of it, you're applying it to the wave function of the Hamiltonian, and maybe you get a number, but you get something other than the wave function back. And now recall that that's garbage. What's kind of funky is sometimes actually the right number pops out. That actually will happen sometimes, but it's just mathematical garbage. So you just forget that. And recall that when that happens, you do it this way, and then you're okay. All right, so that was the big picture. And of course, for momentum and a sine function, the answer was 0 because we actually did that twice in the last class, a few classes anyway. Let's see now what I want to say. Okay. Uncertainty, the one that you always hear on the news is you can't know where something is and how fast it's going. Remember, because I kind of like Stephen Hawking and Albert Einstein stuff, I don't know much about it. I kind of feel like I should. The problem with our total knowledge of how everything works, some people say there's one equation that would replace God and all that. Maybe it's the Schrödinger equation. Oh no, it's not quite right. And the reason is because you can't know where something is and how fast it's going. You can't know where something is does not mesh with the law of gravity, which is essential for like all the Stephen Hawking type of superphysics and gravity and star clusters and all that kind of stuff, dark energy and all that. Quantum and that kind of relativity don't really mesh, and that's why, because you can't know where something is. So that is the position uncertainty position momentum uncertainty principle. And we know that you express that as what we call a commutator Okay, and 0 or not 0, that's the question. Okay, so note that what you're seeing here is just operator 1, operator 2 minus operator 2, operator 1. And on its face, it's like, well, what does that do? Operators don't have meaning unless they're operating on things. So the way I showed you how to deal with that is to operate on a wave function. And what you found was, even on your test, you got this result. Now, again, I told you, this is where quantum gets weird. There are all kinds of operators. You've only seen a few, but there's you're going to have 10 by the time the class is over. There's actually uncertainty principles between a bunch of them. Sorry, I don't think if the commutator is equal to 0, there's no uncertainty principle. If it's not 0, there's an uncertainty principle. So in this case, for position momentum, there's an uncertainty principle because this needs to be 0 and it's not. So that means we have an uncertainty problem. So what do I want to say about that? So, okay, there are a large number of operators. You're going to see about 10 by the end of the class. And there's actually several uncertainty principles. There's an uncertainty principle between angular momentum in the z direction and the x and y direction. So don't write that down. My point is, there's a bunch of these. All right, so this is like the famous one, but there's really a bunch of these. Now, in class and on your test, I showed you how to solve this one this way, but every pair is solved differently. Every pair is solved in the way that solves it, and there's almost no overlap between them. You almost never figure, so I'm doing it this way to figure this out. That's what I'm doing. I'm just using this wave function as a tool. Often that works, sometimes it doesn't. So again, we're going to see that in about a month from now. I just want to let you know that while hopefully you saw that, here I can actually cancel out the wave function was just a tool to figure out that the commutator is not 0, so there's an uncertainty principle. I just use the wave function as a tool to show this. But just be warned, when we have other operators, and I'll show you a few more, I'll show you one more today, you may or may not solve it this way. You just solve it the way that works. And it isn't always going to be to apply wave functions. Again, just some weirdness there. Okay, now there's 3 more things to talk about. Recall that, so here's some, just some dry, non-intuitive equations that say, hey, look, there is or is not an uncertainty principle. Okay, that's all fine. That's like doing your taxes and following that algorithm and just getting a number. You really don't know what the hell, you don't know the tax code just because you did that, right? You don't really necessarily understand the underlying mechanism of our tax system by just doing your taxes and following that little algorithm they give you. And that's kind of what this is like. If you want to know a little bit more about why it works, that's where I had given you that illustration, and is in the handout, of a wide or a thin wave function, and pointing out that you can't do this guy with the eigenvalue way, but the reason that the expectation value way works is because this thing can be turned into sums of functions that are eigenfunctions of momentum, which are just waves. So there was this wave, and again, this is in your handout. It turns out these need to be even functions. Again, I used a computer to solve these. So here's the first 3 waves. And when it comes to the narrower one, you have these same waves, but you end up needing several more of them. And so, anyway. Okay, so the uncertainty comes about because these guys are okay with momentum. This one is not okay with momentum. And again, the magic here is to take this and express it this way. And as I show in your handout right here, so I show you just a bunch of, these are like waves that are okay with momentum. And I show you how, for the fat guy, you only need 3 waves to equal this one. And on the back, I show you, again, these are all done with the computer. This isn't my drawing being manipulated. This is a computerized result. And I show you how you need at least 5 of these waves to get this narrower one. And the uncertainty, that actually is the uncertainty. The fact that I need so many more momentum waves to equate to the narrower wave function is the source of uncertainty, which then brings me to my next point. So what does that mean? Okay, so let me show you here. Okay, now remember that we talked about how, here I'll draw this guy again. Let's draw the wider one. The wider one, which has less certainty in position, but more certainty in momentum. And again, that's because I can recreate it with less with less momentum waves. The way to characterize the uncertainty in position is with the standard deviation, which is, of course, some statistics. But you also, at this point, see, this is why I had to start with. Expectation values. Is this guy here, and I believe the square root, right? Mm-hmm. Yeah. Otherwise, it's a variance. Okay. So that's just a full width half max, right? This is kind of brainless. You can see that there's a certain full width half max here, and if for the narrower one, there's still a full width half max. It's just way smaller. So that's not rocket science at all. Okay. Now, it turns out in grad school, we actually even don't see the proof there. It's a geometry proof. It turns out that, let's see, how do I want to put this? In grad school, let me show you how this works. And I can show some of you, I don't want to do it here. Unfortunately, it really is kind of hideously complicated. It turns out that I can take these wave functions in terms of space, in terms of x, and it turns out that in a process called, now, God, actually, so many of you are engineers. You know Fourier transforms? Some of you have heard that? Okay, it turns out that the Fourier transform, and don't worry about that if you haven't heard of this before. It turns out that if you just simply Fourier transform this, which is just this mathematical operation, it turns out that you can turn the wave function into a wave function of momentum. In other words, I can just simply take this y wave function with x on the axis and turn it into a wave function of where momentum is on the x-axis. And here's what happens. Now again, we learned this in grad school, so I'm not covering it here, but this is how it works. So you have this space wave function turning into a momentum wave function. Now notice what I did. If the wave function is wide in space, it's narrow in momentum, and that's because although I have less certainty where it is, I have more certainty how fast it's going. If I know where it is, if I have great certainty in where it is, I have less certainty on how fast it's going. Again, these are, now for mathematically inclined people, these are actually Fourier transforms of each other. All right, now I should be able to express this. Now I already told you I can express the uncertainty with a full width half max in space, but I could also do it in momentum. And here's how that works. Now the proof of this, by the way, this is a geometry proof. I'll do x in momentum. I'll do x in momentum. It turns out that the standard deviations are greater than half the absolute value of the commutator, which we know in this case is h. Here, let's for space and momentum, we already know what that is.
the commutator is h over I, okay, and the absolute value, actually h bar, right? H bar, did I get that? Did I mess that up? H bar. Okay, absolute value of I, right? Is that weird? Absolute value of I is 1. It's kind of like how something raised to the 0 power is still 1, or the factorial of 0 is still 1. The absolute value of the letter I is 1. It's one of those things that it's definitely correct, but you have to just, if you haven't heard that before, I'm telling you, it's one of those things you have to know. It's kind of like calculus, a question.
The momentum operator, there's nothing after that, so what is it operating on? There's nothing after the momentum operator.
Wait 1 second, hold on. I'm actually bothered right now that this is not complete. So you were asking about, that what was what? That the momentum operator was not operating on something?
Yeah, what is the momentum operator operating on?
Wait, here?
Yes.
No. This is not what I mean. Maybe I should use a subscript.
Oh, it's so
Maybe-
something.
Yeah, I was just, when you were talking about that, that's why I was kind of stammering a bit, because that's what I was thinking of. So here, let me walk you through exactly how to do this, because this is actually on your homework. Yeah, I'm not sure if maybe I'm not writing this out right. Okay, so this is this. So, and this would be this. So imagine that I give you a wave function. You could literally, I mean, not to be too cutesy here, just so that you get it, you could just use a ruler, to be blunt, and just measure this, right? And then you could do this in momentum and multiply the two, and you'll find that it's always greater than half Planck's constant. And the units would work out fine. So Planck's constant is joule second. Planck's constant is a small number, but these full with half max would probably be like in nanometers or even angstroms, right? So anyway, now another thing is that, I'm just trying to be cutesy. I'm just trying to make sure that you get that this is a very knowable thing. But what you do on your homework is, for this, I give you a wave function and you do this, right? And you know how to do this. You know how to do this. You were doing it with Maxwell Boltzmann. I'll give you like a sine or something like that, and you do this. And I'll have a function. It's going to be like sine pi over L times x. In fact, I'm fairly certain that's exactly what it is. And a cheat sheet with all the integral identities. And there you go. Now this is exactly what it's always been. And of course, you know that the operator x is literally just the letter x. X is kind of nice because x is a bit of a friendlier operator, because although you have to write expectation values with the operator in between the wave function, you may recall that we did these a long time ago. What's nice about them is that they're kind of dumb operators. They don't actually do anything to the wave function, so you can kind of just move them out of the way. And then you've got the wave function times its complex conjugate, which is the absolute value squared. And in this case, the same thing. Okay, and again, all you do is, at this point, you look at the cheat sheet on the homework for what the integral identity is. And so you know that if the wave function is sine pi over L times x, then it's just, you're looking for the identity from 0 to L of x squared sine squared pi x over L, and yada 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 over here. Okay, so that gives you this, and now you've got that. Okay, so that's how you do that. And I don't remember, is this on the present homework, this question? I think it is. So seriously, you're doing this on the homework. I don't quite recall if it's this one or the next one. I wrote them all over the summer, so they're not quite fresh in my head. Okay, now when you do this, this is half of it. Now here's the other half. Then you do this. And this is a bit more painful. Not that you haven't already done it. It's a bit more painful because there's an extra operation, which is this. And again, if we're doing like particle in a box, the limits are from 0 to L. And if you're doing p squared, then it again is a little bit harder to set up. There'll be a minus sign from the two i's. And you get a double derivative, that sucks. But anyway, but it's manageable. So there you go. Okay, so with all of this, you then plug it into the formula for uncertainty principle, and you see that it works just fine. That's, again, that's how to do in your homework. So, now remember, so on the homework, and again, because I wrote it, I know exactly what's on it. This is the one that's kind of, you know, these are not too hard, right? These are just, you just set it up and you look at the identity. These take a little bit more work, and this one definitely is going to be like about a page of scribbles probably to get it right. And then you check yourself with the uncertainty principle. The thing I mentioned here, that the sigma x, sigma p, greater than or equal to h over 2. That's exactly what you're going to find. Okay. Any questions on this? No, you're okay. It's a little overwhelming. Again, though, I just want to point out that quantum, as you are being introduced to it, I mean, x sine squared, I mean, that's what you're going to be doing. You're going to integrate x times sine squared. It's not that hard. You did it as undergrads. Sorry, you're still undergrad. Not much longer. But you did it in calc class. It's not that bad. The thing is that you've got all these freaking constants. You've got an I squared or an absolute value of I. What the hell? You got 4 of these things. They have to combine. You can't mess up any constants. Sorry, but you're seniors, right? That's kind of like a senior level skill. Can you take all these moving parts and not mess it up? Because, you know, you guys are designing power plants. So I kind of think, like, from my perspective, I actually really want to know that you can do that for, you know, non-blowing up things purposes. So I think it's fair. But yeah, it's complicated. But, you know, that's you guys, I mean, I don't even know what you guys do. You engineers, you're overwhelmingly engineers. I have no idea what kind of complex things you work on, but I'm pretty sure they all could explode quite readily. And I'm sure you can do this. This just is not that bad. It's just a lot. A lot is not complicated. It's just annoying. Huh? Anything else? All right, so now I wanted to show you one other operator. This would be an easy test question, and it's very simple. And I just want you to get used to the fact that there's a bunch of these. Okay? You've got 3 operators under your belt. You've got momentum, you've got position, we've done that one. You've also got kinetic energy, which could be the Hamiltonian. That's the full Hamiltonian if there's no potential energy, which we're getting to that. Okay, so let's do this one. Let's do P and P squared. Now, normally I would say there wouldn't be an uncertainty principle. So now remember, what this means is that, so we're going to do the commutator, and we want to see whether it's 0 or not. One of the consequences is, you've kind of already seen this, is that when you had a uncertainty with position and momentum, one of the things I was forced to do to solve that sucker was to do this part. So here's like a consequence of the uncertainty principle, other than this jazz right here, is that if I have my wave functions in position, I can still do momentum things. I can still do momentum operator. But if it gets a little bit more complicated, I have to know that I'm actually converting the position thing into a series of other functions that are okay with momentum. So remember that this could be like a sine, and this is e to the ikx and e to the minus ikx. That was an example, right? Remember we did that before. So again, sine is not okay with momentum, but e to the ix and e to the minus ix are. That's a consequence of the uncertainty principle. Again, we tend to cover that more in grad school. I didn't want to harp on that too much. Okay, now I'm going to solve an uncertainty principle for momentum and momentum squared. From what we've covered, the things that are okay with momentum are e to the ikx and e to the minus ikx. Those are the functions that are eigenfunctions of momentum. Can they also be applied to energy, kinetic energy? Momentum squared is basically kinetic energy. Okay, you know what? I'll just make it kinetic energy by dividing by 2 times the mass. And the mass would be like an electron's mass, something like that. It can be anything, but let's say it's an electron. Okay. Now, here's the thing. The consequences are, if this is not 0, I have an uncertainty principle. If that's the case, that means that I'll have a different set of wave functions. Some that are okay with momentum, that's e to the ikx and e to the minus ikx. I already know that. And I'd have to represent those in terms of wave functions that are okay with kinetic energy. They wouldn't be the same. That's what happens if this is not 0. If it is 0, that means that e to the eigenfunctions of momentum, e to the ikx, e to the minus ikx, are also okay with kinetic energy. I can apply kinetic energy operator and get the answer out without resorting to this jazz right here. So that's why it's kind of good to know this stuff. But I have to admit, I'm kind of like right skirting what we do in grad school, and so I don't want to blow you guys' heads off. Anyway, so now I'm going to solve this. As I warned you, the thing is, how? Every uncertainty principle is generally solved a different way. But in this case, it's going to be easy to solve it, to do it the way we did before. In this case, I happen to solve it the same way I did space and momentum. Just happens to be the same good way to solve it. But it is not always that way. Just warning. Okay. So let's write this SOP down. Okay, so momentum, I'm going to do momentum, h over I, single derivative. Then I've got momentum squared, which is my h squared over 2m, double derivative. Okay, then I subtract from that the inverse. I switch order. Notice that I subtract the inverse. Notice that I made that minus a plus, and that's because momentum squared has actually got a minus sign, so I just went ahead and took care of that. Actually, why don't I just do that as well, make it a little bit nicer. Then I've got the double derivative. And then I've got an h over I. Again, I just permuted the order. And then I apply a wave function. And you know what? I can already tell. Can you already tell how this is going to come out? Is it going to be 0 or not? It's actually kind of easy to tell. I really don't need to apply the wave function in this case.
It's easy because h bar over I is a constant. So you can
Right.
outside the integral.
Outside the integral?
Or sorry, outside the derivative.
Right here. You see, folks, you see the things that are in between the derivatives? They're just constants. Those you've had enough calculus. The derivative of 5x is 5 times the derivative of x, right? Right. Derivative of 5x, you can take the 5 outside. It's just 5 times the derivative of x. Okay, so this ends up being minus h bar cubed over 2mi triple derivative. And in case your calc is a little rusty, single derivative in front of double derivative is a triple derivative, that's true, plus h bar squared, h bar cubed, 2mi. And I've got a double derivative before a single derivative, but that doesn't matter. And just think about it, in case you're a little confused, wait, is that true? Well, take all right, so let's say that this was a sine function. Cosine, sine, cosine, right? See, it doesn't matter. Or you can just say, what's the triple derivative of sine? It'd be like cosine. Anyway, Okay, so now you see, this is clearly 0. This is the same thing twice, but there's a minus sign in front. There you go. So actually, I really didn't need to apply a wave function in this case. I can just look at the operators and do some factoring, and the SOBs are exactly the same thing. Not exactly the same thing, there's a minus sign in front of the first one. So anyway, you're okay? A question?
So that means that there's no uncertainty between what? Momentum and energy?
Momentum and kinetic energy.
Okay, so there's zero uncertainty between momentum and kinetic energy based on our derivation of this.
Yep. So now imagine I had a wave function represented as momentum and kinetic energy. If I transformed one to the other, they would be identical. And that's another way of saying, again, I'm kind of dipping into grad school stuff here. What that means is take, remember when I first showed you eigenvalue equations, and I did momentum because that's just a good example. And I said, hey, look, let's apply e to the I kx, right? And let me just do that, in case I'm being a little too abstract. Okay, this ends up being h bar k. Sorry, my handwriting is, handwriting's bad today. Okay, so it gets a pass, right? That's a pass. The operator times the wave function is equal to an eigenvalue times the wave function. That guy is okay. Now that means that when I do this, when I apply the kinetic energy operator, or momentum squared operator, it doesn't really matter. One's just got that little 2m. Okay, now that I have done this, step 1. Step 2, e to the I kx is okay. That means this has to work. I don't know that because I haven't done it yet. But if this is 0 and this works, this also has to work because there's no uncertainty. Okay, so let's see. I squared, k squared. I squared is minus 1, so that's h squared, h bar squared, k squared over 2m. Of course, no matter how many derivatives of e to the I kx you take, it's always there. Pass? Right, pass. Right, pass. It passed. There you go. So again, that's just another example. Okay, there's one more, and then I guess we can stop there. And you can kind of predict this one. You can predict this one based on just some general calc, just like you did with momentum and kinetic energy. I want to do position and kinetic energy. Let's do that one. And it's really probably at this point just good calc practice. Let's do position and kinetic energy. And remember, don't ever let the little hat fool you. That doesn't mean anything. And I'm going to apply a wave function to it. Again, this is an easy way to solve this one. We actually really do need to apply a wave function. And again, you don't always do it that way. I just can't emphasize that enough because when we get into rotation, they get a bit harder. So let's do this one. Okay, so I have, remember x hat is just an x. There's no magic to that. Minus h bar squared over 2m, double derivative. Let me go ahead and do the little, pass the wave function through. Okay, and then I just permute that. Minus h bar squared over 2m. Minus plus. What am I doing? Double derivative? Yeah, double derivative. Right, this is the kinetic energy operator. But then I've permuted the deal. Okay. Now, what I can already tell, can anyone guess why I can tell I'm not going to find 0 this time? Can you tell how that's going to come about? Yeah, I heard one of you say, begins with the P. Right, you're going to have a product rule. That's the thing that's going to screw you, by the way. Okay, now notice that there isn't much to do here. I've got some constants. I'm doing the first term. I got some constants. Then I'm just gonna put an x times, let me use some symbology. Are you used to the symbology? This means double derivative. Okay, if you haven't, then this is double derivative. It's very useful, especially because we're going to be writing this across the board. Okay, now let's do the next thing. I always do these slowly, right? Because it's way painful not to. Okay, first derivative of x, that leaves that guy alone. Right, remember, do the derivative of one, leave the other one alone, and then vice versa. So I did the derivative of that one, I left that one alone, vice versa. Okay, x. Okay, and again, I'm using my symbology. Again, I'm not using the board super well, so let me just move over.
Why is the x not included in the derivative on the left-hand side, but it is on the right?
Wait, huh? Well, hold on, there's a double derivative here, but the x is over there, it's to the left of it.
Yeah, why is that again?
Well, now that's the formula for a commutation.
Okay.
Operator, the order matters. Remember, another way to think of the uncertainty principle is I make a measurement in position, and then I measure the particle's momentum, and I get answers. But if I went back in time and I did it the other way, I would have gotten different answers. And not because like I did some paradox and I killed my own grandfather. It literally, another thing you hear about quantum mechanics is that the measurement affects the result. Have you ever heard that before in quantum mechanics? The measurement perturbs the system and it changes it. That's actually the uncertainty principle, by the way. And that's why, in this case, we're not going to find zero, by the way. So it matters. X in front of the double derivative means that you avoid a product rule, right? Now notice also, it leaves you in kind of a weird position. Remember, X is a dumb operator. It just sits there. It doesn't do anything. And when you run into that, don't make it do anything. It's already done what it's meant to do. Okay, I can see that I'm still, this guy's the hard part. So let me just rewrite the first part of the commutator when I did X and the kinetic energy. So I'm just rewriting that. Okay, now I need to do the next step. Okay, the next step is, okay, I've got the single derivative, and then I've got another product rule, which is why this sucks. Let's see, I'll do what I did before. I'll take the derivative of X, and then I'll do vice versa. Okay, so yeah, you see that? You see that? So I can already see. So there's that. Let me do the third term. Notice that these just cancel. And again, it is so these just got wiped out. And what I am left with is this. Okay, and then I will just write this out to be thorough over M. I'm just going to take that, just forget the 2. Okay. So therefore, the commutator of position and kinetic energy is not 0. Now, this is why I like this question. I've been telling you it's either 0 or not 0. It's either 0 or not 0. What do you think of that? What do I do with that?
It just depends. I mean, you could just say it's not 0.
There you go. Right. And remember, as much as this stuff sucks, I shouldn't say that, but this stuff sucks, you can be very absolute with this. I said either it's 0 or not 0. Well, that is complicated, but it ain't a 0. Besides, the derivative of wave functions, now if you wanted to be like, well, I'm just really not sure about that, plug sine kx in. Is that 0? No. The only thing that would be 0 is a constant in our wave function. Since I've been teaching this class, I've never had a wave function that was just h bar, so that wouldn't do anything. So no, this is in fact not 0. So I kind of like this question. I like showing this because it's kind of cage rattling to see that a commutator What it means to not be zero can mean a bunch of different things, including that it's a derivative. But again, to be very absolute, it just isn't zero, and that's all that matters. A question? Question? Yeah.
What is the implication? If it is zero or not zero?
If it's zero, that means there's no uncertainty. So what this implies is, the more certain you are in position, the less certain you are in kinetic energy. Now, there's actually a consequence to this. By the way, let me show you one. It's a chemical one, and I know we're out of time. There's these types of dye that are used in bioimaging. There's a type of dye used in bioimaging. It's called the cyanine. Looks like this. And then there's, I'm probably drawing that wrong. Okay, so it turns out that if N is big, the dye is red. If N is small, the dye is blue. Okay, tell you what, I'll explain this a little bit more next time. But what's happening is the electrons in here, if the electrons are small, then you don't really know where they're at. That means that you have minimal understanding of position. It means you have good understanding of position. Sorry, if N is small, that means that the electrons in this conjugated double bond are very localized. But that means that you have less certainty in energy. And that means that it emits at higher energies. If this is very long, you have very great uncertainty in where the electrons are, but that means you have greater certainty in energy, and that's what makes it red. I know that doesn't make sense from what I just shown you. I'll explain this part next time. So next time I'll talk a little bit more about the consequences of uncertainty. Anyway.